Hello everyone and welcome back to the Hardware City channel. So glad to have you here again. Today I'm going to fulfill a promise that I made in last episode. You maybe remember in the last episode I told you something about coherers and coherer mysteries and an yet unknown effect with coherers that are producing noise. And it's a strange thing because passive elements like coherer normally don't produce noise. And by the end of the episode I told you I would show you a setup, a classical coherer setup, where we will do the classical thing a coherer is supposed to make for, the reception or detection of radio waves. And I told you I won't do this in the classical way with a metal filings coherer, as everyone does. Everyone is doing here on YouTube. I wanted to show you a very special coherer, the Branly Ball Coherer, and yeah, that's what I'm going to show you today. Okay, at first sight the Branly Coherer seems to be a little curious because it isn't made out of metal filings like this. This is iron. These are iron filings. It's made of steel balls like this. These are 8mm steel balls, and what Branly did, he arranged those balls as a string like this and applied a very slight pressure on those balls that they had a very loose contact among each other, and then you observe the same effects as other researchers did before him with the metal filings coherer. That seems a little bit strange when you think about it, but when you look at those metal filings here, you see there are a lot of small particles here, and I already told you that the coherer effect somehow is linked with the quantum tunneling effect. That means that those metal filings here are covered with a very thin layer of, let's say, contamination. This could be oxide, it could be sulfur, it could be grease, something that is non-conductible. And this is an isolation barrier between all those filings, and the coherer effect means that somehow when an energy radio wave hits those filings here, these barriers are facing a breakthrough. So electrons suddenly can flow from one side to the other, depending on the place where the electrodes are, and a current is flowing. So the system is going from a high resistance state to a low resistance state. And in fact, a steel ball is nothing more than a very big particle. So we have a bigger size, but the principle stays the same, because you have a very loose contact, you have a contamination layer, you have oxide or grease, for example grease from our hands here, on the surface of those spheres, and this gives a very small insulation barrier, and this can be disrupted in the same way, or the electrons can undergo it in the same way as in the metal filings coherer. So what we need now is a proper test setup to arrange all those steel balls in some kind of string and apply an adjustable pressure on each side where the electrodes are. And I'll show you now how I made this. So this is my setup, this is my coherer receiver. I will explain you in short all the elements and components that are inside this design. Here is the coherer place. I show you in more detail how I made this. And you can see here two elements. These are metal rods with copper tubes at the end. This is the receiving circuit, namely a dipole antenna. And here you can see two wires running from the coherer down to the lower assembly. These elements here are radio chokes, radio frequency chokes. That means inductive elements that prevent radio frequency from floating down this way, so that the radio frequency that was received by this dipole here is concentrated in the coherer. So we minimize the energy loss.
so that the coherer gets all the energy that these circuit here, these dipole circuit is receiving. In the lower assembly there's nothing special. We have a resistor here and an LED and two connectors here to apply DC voltage for about 5 volts, 6 volts.
Now one may ask, what do we need those dipole rods here for? This is because the coherer is not a receiver. The coherer is an element that reacts to radio wave energy, but it cannot receive the radio wave energy itself. So when you are want to receive radio wave energy, then you always have to apply an antenna. An antenna that is suitable to receive radio wave energy in the frequency band that you want. And so it's very good to obey the laws of physics. When you have a dipole like this, these are two rods with the same length, then there's a rule in physics that was first theorized by Mr. Maxwell and later proved by Heinrich Hertz. We have two rods here, and you can take the received radio energy here between those two rods in the inside, and the frequency that you can receive is directly related to the wavelength, and the wavelength is calculated in a way that the total length of this dipole from this point to this point is always half of the wavelength. This has something to do with the distribution of the current that is induced here in this antenna element, and the current here on the inside is a maximum and the outside is a minimum, because the conductor here is ending, so normal current can flow here to the outside. It's impossible, so the current here is going to zero and here at maximum. So we have a, let's say, half wave, sinus shaped wave. It's going from here up to maximum and then down here again. This is half of the wavelength of the frequency you wanna receive. So for example, if I have here a dipole that has 10 centimeters from here to there, then the wavelength I can receive is 20 centimeters.
So this is exactly what you can see here. You have here those two rods of the dipole, and at the end here I have some copper tubes I soldered to the end. This is something to do to add some more electrical capacity to the circuit. Electrical capacity, or a capacitor, an electronic, is an element that can store electric energy. And I did this for two purposes, because with these two copper tubes here at the end, we are in fact realizing a capacitor that is applied at the end of the dipole rods. And first, this adds some more capacity to the circuit so it can store more energy. And the second thing is that we decrease the receiving frequency a little bit, because the capacitor at the end of the diode is working as some kind of virtual enlargement of the dipole rods. So we can receive a radio frequency that in fact is a little bit lower than you would normally gain by the specified length of the diode, of the dipoles here. And a little bit lower frequency is a good way, because you higher get in the frequency, the more problems you get, because a lot of elements you are using in the high frequency technique behave different when the frequency gets higher and higher. For example, an inductor suddenly can turn into some kind of capacitor due to parasitic effects, and vice versa with the rising frequency. So it's always good when you can keep this frequency, let's say, below 1 gigahertz. Then you are in a more or less safe range. So this is the second reason why I applied those copper tubes here. Now we take a look at the coherer itself. You can see here it's made of plexiglass tube. In the plexiglass tube you can see the steel balls, nicely arranged as a string. And here I have two electrodes. These are just parts of aluminum. I cut it on a lathe. This is the first electrode here, And this here is the second electrode. It's a little more complicated, mechanically complicated, because I applied here means for adjusting the pressure on the string. You can see there's a screw here, and the screw is moving a piston, this one here. And here you have a spring, and here a second piston. So you can finally adjust the mechanical tension of this spring here, and this tension is directly applied to this string of balls. So it's a good way to adjust the mechanical pressure. So both electrodes are connected to the dipole rods on this side and also on this side here, and the energy here is directly going into the coherer. And you know, we need to apply DC voltage to the coherer to make it switch through, and this voltage is supplied via these two radio chokes here. These are two coils with air cores, so they're quite suitable for the frequency range. And the DC path is routed down here, and here you can see it's a standard serial wiring. You have one pole, the plus pole is connected here, it's going through the LED, then through the coherer, coming down again through this resistor, and then going to ground. And that's all. Of course, for testing a receiver we need a suitable transmitter. Something to emit enough radio energy to make the coherer work and to see if the LED really goes on or not. And this here is my transmitter. So how does a transmitter work? Well, that's not so hard to understand, because it's the same principle I showed you on the receiver, but vice versa. Again, you can see a dipole consisting of two rods and the copper tubes at the end. So this is very important to make this dipole in the same way as I did in the receiver, because when the mechanical dimensions are not the same, then the tune frequency is also different. And when both antennas of the transmitter and receiver are not tuned to the same frequency, then we won't get a proper connection between both. It's logical. So here you can see this is a piezo element from piezo lighter. When you push this, it generates a spark, an electrical spark, and the voltage here of the spark is going through these two radio frequency coils. It's the same coils as I applied in the receiver, and the reason is also the same. The radio wave energy that is generated here shall not leak out here through the coils in the piezo element. It should stay here and be radiated. This is the reason why I applied those chokes. And here you can see two steel balls soldered on a piece of wire. And this in fact is the spark gap. This is the same principle that Heinrich Hertz applied when he made his first experiments. Now, how does it work? Well, it's pretty easy. When we push this button here, then voltage spark and an inrush of electrical energy is generated and is floating here in this antenna dipole element. Because now we have a huge voltage on one side here, namely this side, and a lower voltage on this side, then a spark is generated. It's flowing from here to there. The spark, in fact, is a very short electrical connection that is established between those two rods. So the high tension that is here on this side is generating a huge current flow through the spark that is working as a conductor element. So the energy is flowing with a high current from this side to this side. And because everything has some kind of inertia, the flow from one energy is going completely to the other side here, and then the spark gets extinguished, so that the energy that's gone from this side to this side stays here for a moment, and then the same thing is happening vice versa. Now a spark from here to there is jumping over, re-establishing the connection, and the energy is flowing back to this side. So in fact that means the energy is oscillating forth and back, and that means the current is flowing in the same way, And the frequency is specified by the mechanical dimensions of this dipole antenna and the capacitor elements here at the end. And every time the current is going through these rods, radio waves are radiated through space. And so an energy wave is going away from here through space, and after some meters is hitting the antenna of the receiver. Now I hope you can see the spark. It's a tiny little one. I don't know if the shutter frequency of the camera is good enough to make the spark visible. At least as I can tell you, there is a spark. Okay, now I connected a DC power supply of 4 volts to the coherer, and now I switch on the supply. You can see we have a glowing here of the LED, so that means it's a conducting state. So let's tap a little bit. Okay, now it's off. So now the coherer is in the receiving state, and now I take my receiver here, and let's first try a very short distance to test. That's about a half meter, and you can see the LED lights up. It's not so easy to decohere. Maybe we should lower the pressure a little bit. Yeah, okay. And now it works good. Okay, and now let's try if we can reach if we can bridge a bigger distance. 3 meters. Okay, here we go. And it works. And now we bridge 5 meters. That's the maximum I can get in my flat. It works. Now, bridging a distance of 5 meters and maybe even more with such a simple design, I think is really impressive, and it's really going beyond my expectation. But what you can learn here is that's not a good way just to put some balls or metal filings together and wiring it with a resistor and an LED, apply some voltage and then freaking around with the piezo lighter. That's not the good way. You always have to obey the rules of physics, so making a proper design, think well about what you are intending to do and obey the rules of physics and high frequency, and then you will get success. So, thank you folks for coming in, and I see you again in the next episode of the Hardware City channel. Thanks and bye.